Real exam questions. This is question 60, dealing with slab design with the method equal deflection. A rectangular slab is fixed on 4 sides in walls with a thickness of 40 centimeters. The load in ultimate limit persistent is 40 kilonewton per square meter, including its own weight. Concrete quality is C2530. The slab is 200 millimeters thick and has a concrete cover of 30 millimeters. Determine the upper and lower reinforcement using the method of equal deflection. Only bars with a diameter 12 are available, and determine the necessary spacing of the bars within 1 millimeter and determine the number of bars per meter. When you make a cross section like this, we have the situation that the slab is clamped on both sides, and then the bending moment does something like that, with a positive bending moment in the B direction and a negative bending moment in the B direction. The definition here is that bending moment is positive when there is tension on the lower fiber. Cross section in the other direction gives you MA negative and MA positive. And to identify the positions of the reinforcement, this is a slab of 200 millimeters with the concrete cover 30. It's only diameter 12 that we may use. And then, of course, you will have MB negative and MA negative, MA positive and MB positive. So first, we look in the A direction. The net span is, of course, equal to the clearance, which is 6.3 meters, plus 2 times the minimum of half the thickness of the slab or half the thickness of the support. So this is here 6.5 meter. So that's where this is pointed out as 6.5 instead of 6.3. In the B direction, we got 5 meters plus 2 times, again, the minimum of 0.2 divided by 2 or 0.4 divided by 2 gives you 5.2 meters. We know for the formula of equal deflection, you can easily prove this equation, is QA over Q is equal to 1 over 1 plus omega A omega B multiplied by A over B to the 4th power. We fill in the right numbers. We know that omega A and omega B, they are they cancel each other out, or they are 1. For this type of situation, omega A and omega B is 1. Then we can fill in the parameters, and we got QA is equal to 0.2906 Q. And Q is 40 kilonewton per square meter. And then QA, of course, is 11.62 kilonewton per square meter. So that's the force, that's the load in the A direction. The negative bending moment at the edges of the slab is then Q8 squared over 12, which is 40.92 kilonewton meter per meter. And the positive bending moment is Q8 squared over 24, and it gives you 20.46 kilonewton meter per meter. Now we will have a look in the B direction. We know that A was 6.5, B is 5.2 meters, that's the effective length. Omega A and omega B is 1 because of the situation in direction A and B is equal, and also because omega A is 1 because of the fixed end support. Q was 40. We apply the formula of equal deflection. QB over B is equal to this. So you see that in this formula, cyclic permutation took place if you compare it with the formula on the previous slide. When you calculate this, we have 0.7094. So multiplied by 40 gives you QB, which is 28.38 kilonewton per square meter. The negative bending moment is QB squared over 12. It's 63.95. And the positive bending moment is half of this, is 31.97. Now, we will order all those bending moments with the largest bending moment on top and the lowest on the bottom. Why do we do that? Because you will try always where the bending moment is the largest to use the largest effective depth. You try to do that so it's more economical to put your reinforcement. So you start with the negative bending moment in the B direction, which is the biggest. So the lever arm is the total depth of the slab 200 minus concrete cover minus points of gravity. So you see here, so there's 12, half of the diameter 12, which is 164 millimeter. The reduced bending moment for the negative bending moments in the B direction is then M divided by B d squared FCD. FCD is 0.85 times 25 divided by 1.5. The material factor gives you 0.1678. The negative bending moment in the A direction there is now in the second reinforcement layer, but on top of the slab. And the lever arm is then, of course, the same as this minus the diameter of the reinforcement in direction B, which gives you a total effective depth of 152 millimeters, and the reduced bending moment is then equal to 1.125. Then the positive bending moment in the B direction, which is here at the bottom. The first layer has a lever arm of 164, and then we can calculate the reduced bending moment in this direction. And MA positive is on the lever arm of 152 millimeters, and the reduced bending moment is 0.0625. So now we have all the different reduced bending moments. In domain 1B, we see it immediately when you have the ease of use of the tables. You know directly where you are in mu d for B negative is 0.1678. So it's somewhere here, and all other values are smaller. So from there to there, this is domain 1B. The first part is the domain where the parabola, only the parabola relationship is used. And this is the section where the rectangular relationship is used. So 0.1678, we make an interpolation for zeta and to find the reinforcement, and zeta is 0.9033 between those two. And the reinforcement, of course, is then the bending moment divided by the lever arm divided by the yield strength of the reinforcement, and gives you 929 square millimeter per meter. Then we look at MUD for the reduced bending moment for the negative bending moments in A direction. Between those two figures, interpolation gives you 667 square millimeter per meter. And then we do the same for MUD in the positive bending moments in the B direction. And then at last for the positive bending moments in the A direction. Now, one can wonder, why are we calculating the zeta? And in previous videos, we used zeta as 0.9. Don't make it a mistake to it. For yield lines, we use the zeta equals 0.9 because this is an upper bound method. And for equal bending, which is a lower bound method, we have to calculate the lever arm according to the concrete tables. Now, the needed reinforcement of the negative bending moments in the B direction was 992 square millimeter per meter. when we see that we only use diameter 12, so the total cross section is then 130 square millimeters. So that means for this value that diameter 12 center to center equal to 114 millimeters. And this means that you have 8.8 bars per meter, and then we round it off to 9 per meter. For the negative bending moments in the A direction, we do the same. We convert it into center to center distance. It's 169. This gives you 5.9 rebars or 6 per meter. And in the B direction, we got 5 per meter, not 4, because you always must end up with a larger number than this number. And then for the positive bending moments in A direction, you have 3 diameters per meter. Now take care, this could always be bigger than the minimum reinforcement. And the minimum reinforcement for a slab of 200 millimeter is around 205, I think, square millimeters per meter. So this is okay. If not, you must replace this by minimum reinforcement. So to summarize it now, this was the plan view of the slab. That is where the reinforcement is going when you make a view by cutting it like that. And then you see it's all diameter 12, top reinforcement is 9 per meter, second layer 6 per meter, and the reinforcement for the positive bending moments is 5 per meter, and in second layer 3 per meter.